Okay, so this video is to summarize our discussion on mechanical advantage and basically mechanical advantage in chain and belt drives, which is bicycle. So let's just see what is mechanical advantage. Mechanical advantage is the factor by which the input force is multiplied by a machine. So if you are applying a force F, if that becomes F multiplied by something, that factor is called as mechanical advantage. Mathematically, it is the ratio of the force that is supplied by the machine and the force that is supplied into the machine, or output force upon input force. So mechanical advantage is very simple: output force upon input force. Now in case of a bicycle, what is the output force? So as we know that in the case of the bicycle, there is only one force that is making the bicycle accelerate, and that's the only force that is acting on the bicycle from outside, and that is frictional force. So what is happening in the bicycle is that the system somehow is designed in such a way that the moment we apply force on the pedal, it generates an external force which happens because of the friction, and this frictional force is our output force. So what do we need to do if we want to find out the mechanical advantage? We need to understand that if we are applying some force on the pedal, how much force is actually being supplied to the bicycle in terms of friction, and the ratio of this frictional force and the force that we have applied would be our mechanical advantage. So this is a diagram where you see that the pedal is being pushed, and that's the input force which we are supplying, and then ultimately it is the friction because of which the bicycle moves forward. So if somehow we can calculate the ratio of the friction force and the input force, then we have calculated the mechanical advantage. So as we have already seen, mechanical advantage is F output upon F input, which in our case is friction upon the force that we are applying on the pedal. Now let's just check this diagram. So what we are seeing over here is a sprocket. This is the front sprocket, and this one over here is the radius of the front sprocket. This is the pedal, and this is the radius of the pedal. There is this chain connected to the front sprocket, and then this chain connects to the rear sprocket as well, and there is a tension in the chain, and that is we will call that FTC, or force due to the tension of chain. Now if we want to find out mechanical advantage and a relationship between F output and F input, let's take some assumptions. So the first assumption that we'll take is that there is no acceleration, which means that this is already, moving bicycle. It's moving already, and it is not accelerating. Whatever angular velocity or translational velocity is, it stays as it is. So it doesn't change, and which means there is no acceleration. Now, if that is the case, that means that whatever force is being applied by the pedal, whatever torque is being applied by the pedal, must be equal to the torque that is applied by the chain. Since both the torques cancel out each other, we get zero angular acceleration. And that is what we have written over here: force of pedal multiplied by the radius of pedal. This is the radius of the pedal, which gives us the torque because of the pedal. This must be equal to the force of the tension in the chain multiplied by the radius of the front sprocket. And this gives us our first equation, which is force of pedal upon force of tension in chain is equal to the radius of the front sprocket upon the radius of the pedal. This is the front sprocket radius, and this is the radius of the pedal. Now we have already got the force of pedal as our numerator. What do we want? We want the denominator as, the force of pedal is basically what we want, force of pedal to be a denominator. So we will try to get another relationship where we get the force due to friction as well, and then we'll try to manipulate it in such a way that this force of friction and this force of pedal comes into one ratio, and then we'll see what is on the RHS, and that would be our mechanical advantage. So let's go to the rear wheel and see what is happening. Now, as we have seen that there is no acceleration. So in the rear wheel, the same thing happens again. There is this tension force which is applying some torque, and then there is this friction which is again applying some force, and because of that torque. So the torque because of the friction is in the anti-clockwise direction, the torque because of the tension in the chain is in the clockwise direction, and they cancel out each other, resulting into no acceleration, which results into this equation FTC, which is the tension into the radius of the sprocket multiplied by F friction into the radius of the wheel, because friction is being applied over here, so we'll have to take the entire radius, and this gives us this ratio, which is the force of friction divided by the force of tension in the chain is equal to the radius of the rear sprocket and the radius of wheel. So now you have got your force of friction as a numerator. So what I'll do now is I'll just divide the equation 2 by equation 1. That would bring the force by the pedal in denominator, and this is what I get. So when I divide equation 2 by equation 1, this is equation 2 and this was equation 1. So when I do that, I get my mechanical advantage as the radius of rear sprocket upon the radius of front sprocket multiplied by the radius of pedal upon the radius of wheel. We will see that this ratio has a name, has a specific name, and so is the case with this ratio as well. And this is our mechanical advantage. But before doing that, let's just see another approach, and this approach is basically the work done approach. Now we know that since there is no change in kinetic energy, so the net work done in the system is zero, right? So the work done by the output torque must be equal to the work done by the input torque. So the input torque is basically the torque which is due to the force by the pedal, and the output torque is the force that is because of the friction. So there is no change in kinetic energy, and hence the net work done on this entire system must be zero, and hence these work done should be equal. So how do we calculate work done? The work done is calculated in this case using torque multiplied by angular displacement. Torque is force into radius and then the angular displacement. So we calculate the work done for pedal and then we calculate the work done for friction, right? And this theta is the angular displacement of the front sprocket, and theta rear is the angular displacement of rear sprocket, and they are not going to be same, and we'll see why. So what we are seeing over here is that in this diagram, if you check, this is one single chain. So which means the point B and the point A, the velocity at point A and velocity at point B must be same because they are moving together, right? And they are one single system. So there the velocity has to be same. And if VA is equal to VB, because this is the same chain, hence the angular velocity of the front sprocket multiplied by the radius of the front sprocket must be equal to the angular velocity of rear sprocket multiplied by the radius of rear sprocket. And this gives me the relation between the angular displacement of the front sprocket upon the angular displacement of the rear sprocket, which is the ratio of rear sprocket. So overall, what does this say? This says that the larger the ratio of the rear sprocket and front sprocket is, the lesser the front sprocket would have, the lesser displacement we will see in the front sprocket. Let me just show this to you using a diagram. And here is a diagram. As you can see, in this case, the rear sprocket is a very small one and the front sprocket is a very large one. So what do we see? When the front sprocket is larger, much larger than the rear sprocket, then you have more angular displacement for the rear wheel, right? And very less angular displacement comparatively for the front sprocket. However, in this case, when you check, the front sprocket and the rear sprocket are not, the difference in the radius is not as huge. So for the same displacement, you have now comparatively lesser angular displacement for the rear wheel or the rear sprocket. So overall, if you decrease this radius, the angular displacement over here increases. Or we can say that if you want to go to a higher gear, you basically would have to reduce this radius. You will have to reduce this radius, which is the radius of the rear sprocket. If this gets reduced, you basically cover more angular displacement, and that would result into more speed. Okay, so anyways, we have come up to this formula. Theta fs upon theta rs is equal to rs, which is the radius of rear sprocket upon radius of front sprocket. Now what do we get? So we already had from the earlier equation 1 that this front the force due to friction upon the force due to pedal is equal to r pedal upon r wheel multiplied by the angular displacement of front sprocket upon angular displacement of rear sprocket. And this we have already calculated in equation 2. So just let's put the values that we have calculated in equation 2 into equation 3, and this is what we get. And this is again the same result that we have got. So this time we've got the same result, but the approach was different. This time what we did, we just ensured that we are now equating the work done due to the torque in the front and the rear sprocket, and that has to be same because there is no change in kinetic energy. Okay, now let's just try to decode this. Now let's just understand what is this r pedal upon r wheel. So this r pedal upon r wheel is actually called the crank wheel ratio. Similarly, this r rear sprocket upon r of front sprocket is called as the gear ratio. In fact, the gear ratio is also defined as the angular speed of the input gear upon the angular speed of the output gear. Since the angular speed of input gear is inversely proportional to the radius of input gear, so this gets reversed, and overall you can also write mechanical advantage as crank wheel ratio multiplied by gear ratio. Now if you check over here, this gear ratio is nothing but, we have just seen that this gear ratio is nothing but the radius of output gear upon the radius of input gear. Now we have seen most of the cases the input gear is actually a little larger than the output gear, but if you have a very low gear, which is possible in the geared bicycles, then you can have your gear ratio greater than 1. It is possible in some cases. But as far as the crank wheel ratio, which is the ratio of the length of the pedal and the ratio of the wheel, it is highly unlikely that this is going to be greater than 1. So most of the times you would see that both your gear ratio and crank wheel ratio are lesser than 1, and your mechanical advantage is also lesser than 1. Even if your gear ratio is greater than 1, because the crank wheel ratio is lesser than 1, the mechanical advantage most of the times remains lesser than 1. Okay, and in fact, as an additional information, it is only when the mechanical advantage is greater than 1, it is only in that case when you are tying a rope to the pedal and then trying to pull the bicycle back, the bicycle is going to actually move forward. Now this is an information that we have to verify, so maybe next time we would try to verify that, but we have read it that this is what is the case. If you get the mechanical advantage greater than 1, ultimately that is going to make your bicycle move in front, even if you are pulling it backwards if using a rope tied to the pedal. Now what are the conclusions? The conclusions is, from this entire discussion, the lower the gear, the longer the rear sprocket radius, and which is of course obvious. The lower gear means that this small circle becomes large, so the longer the rear sprocket radius and higher the mechanical advantage. Higher the mechanical advantage as the front sprocket radius is constant. This remains constant. This becomes larger, and as we have seen that the ratio depends on, the mechanical advantage depends on the ratio of the rear sprocket upon the front sprocket. And so if you make it large, you are going to get more mechanical advantage. Secondly, mechanical advantage is generally, which I just discussed, lesser than 1. We need a very large radius of the rear sprocket to get a mechanical advantage of greater than 1, which is very rare. And higher the mechanical advantage, lower the speed. So which is what we have also observed, that whenever there is a lower gear, the bicycle actually travels slower, and that is something that can be seen over here as well. If you have a larger rear sprocket over here, then this angular displacement is going to be even lesser, and hence the bicycle is going to move slower. Okay, now an additional advantage information. If you are riding a bicycle, and in that case, the friction on the front wheel is always opposite to the direction of motion, and that is because the front wheel, this is our front wheel. I hope it is visible. This front wheel is not connected to anything. The reason that it is moving is because of friction. And if the bicycle is moving in front, the friction has to act in this direction, the opposite direction, and otherwise the wheel is not going to turn in the right direction. So if a bicycle is moving in front, the friction in the front wheel is acting backwards. Okay, so this is it as far as mechanical advantage and our discussion on mechanical advantage in chain and belt drives is concerned.